This is the solution video for problem set 7, problem 2, which is the serial comparator problem. And essentially, rather than restate the problem, I'm just going to draw the block diagram that I have in mind where I'm going to do this. So essentially, we've got a register X, shifting data, and our register Y is shifting data into a state diagram or a state machine that has a single comparator cell somewhere inside of it. And so basically these are going to go inside. The bit that we input is going to somehow go into this comparator, go into a state. Somehow we've got some kind of state machine here, and then we're going to output that information, the final comparison, into our output register, which I'm going to say is Z. So that's kind of what I've got pictured in mind. So there's a single comparator cell that we're going to design, and we're going to design the state machine for what's going to happen inside there. And so all we need to know is whether or not X and Y are equal. We do not need to know if they're greater than or less than, unlike some of our previous comparator problems. So basically I'm going to start from my assumption that I want to basically figure out how these compare first, because that's a really easy solution. So I've got X sub I and Y sub I being inputted, and I'm going to have their comparison. So I'm going to call this variable E. Are they equal or not? So if they're equal, they will be 1, 0, 0, 1. So this is when they're equal, and this is when they're not. So I'm going to make this the input to my state diagram, because this basically sums up everything I need to know about that. And so what do I need to remember inside my state machine to actually make this work? Well, I need to remember where y sub I minus 1 and x sub I minus 1 equal, and where y sub I minus 2 and x sub I minus 2 equal. I don't really need to keep track of any other information. And so what I'm going to create may not be the most minimal circuit, but it will be a very expedient circuit. And so E is just going to be equal to x sub I and XOR y sub I. And so we're going to start with the assumption that we're going to basically have our states, and we're going to need to have a state. We're going to start in a state. We're going to say 1, 1 to say that the previous two bits are equal. So we're going to, I'll explain my reasoning here in a second. So this is going to be my state encoding. And this will also be my state name. And the meaning will be x sub I minus 2 equals y sub I minus 2, and x sub I minus 1 equals y sub I minus 1. This will be x sub I minus 2 does not equal y sub I minus 2. So that's this one. And this is x sub I minus 1 equals y sub I minus 1. This is going to be x sub I minus 2 equals y sub I minus 2, and x sub I minus 1 does not equal y sub I minus 1. And here, x sub I minus 2 does not equal y sub I minus 2, and x sub I minus 1 does not equal y sub I minus 1.